All right, hello everyone. Thank you very much for inviting me to speak, and congratulations on this very impressive achievement of the first International Center of Excellence. I'm going to give you an overview of VAM, ventilation air methane, and I'll cover quite a lot, so I'll do it pretty quickly, so that you get an impression of what this is all about. So the questions I will basically be answering is, what is VAM? Why is VAM an issue? And why is VAM a climate opportunity? We'll cover a bit of technologies for processing VAM, especially the proven technologies so far. There are a number of technologies in the making, but not so many proven. We'll look at successful installations, finally guidelines of feasibility, and a bit about VAM in Poland. So what is VAM? Well, when coal is formed, so is methane. So when you excavate the coal, you will release methane. Now the problem is that VAM, or methane, in air is explosive when the concentration is between 5 and 15%. If it's lower, you're okay. You can have a spark without an explosion. And if it's higher, you can also have a spark without explosion. So therefore, methane is drained prior to and after excavation. But even though if you have extensive drainage from the coal seam, you still have a lot of methane coming out when you excavate. So what you do is you push ventilation air through the mine to reduce the concentrations to safe levels. So the VAM concentration would typically be below 1%. So this is a principal image where you have the drainage gas before the excavation, and there you can have very good concentrations, meaning 30% or higher, and that is easy to use for example, generation of electricity. But then you have the large volume, and we're talking like 70% of the total volume coming up in the ventilation shaft in extremely low concentrations. So you've solved the safety problem by reducing the concentration below 5%, but you have very large flows with ventilation, and that means very large total emissions. And since we found out that methane is a greenhouse gas, that is a problem. So if you look at the emissions in very low concentration from a big mine shaft, that can be as much as 50,000 tons of methane per year, which corresponds to 1 million tons of CO2 equivalents. So the impact of this emission is similar to the emissions from 1 million cows or from 500,000 cars. And the difference being that it's a single source of emission. So by processing or cleaning the methane in ventilation air can have the same effect as removing 500,000 cars from the streets. So looking at the effect, you have the earth, you have the atmosphere, which is thin. It's comparable to the skin of an apple. And since you have CO2 in the atmosphere, you have a greenhouse effect. So it maintains some of the sun's radiation heat. So instead of minus 15 degrees on average, you have plus 15 on average. Without CO2 in the atmosphere, we would have a frozen planet. Now, when we increase the CO2 content, that means that the CO2 will contain more of the sun's heat in the atmosphere. So this is an illustration of CO2 in the atmosphere, and you can see they radiate a little bit of heat. And if you compare that to methane, methane contains much more heat. So comparing the two, I mean, there are a number of greenhouse gases, so normally you relate to CO2. So you set the CO2 to 1. And in comparison, the most widely used factor for methane is 25. So a ton of methane equals 25 tons of CO2. Now the lifetime in atmosphere is also important. CO2 is an end product, nothing more happens to it. So lifetime in atmosphere, tens of thousands of years. So for us, forever. Methane, within around 12 years, it oxidizes and turns into CO2. Now methane, CH4, is the second most important greenhouse gas. It's a much more powerful greenhouse gas than CO2, has a short lifetime in atmosphere, so the emission reductions can be quick and positive. And also, methane is very interesting since it generates energy when abated or when oxidized. A brief comparison, it's quite confusing when you compare different greenhouse gases, and this is a way to try to explain this. The upper two diagrams show that the impact of CO2 is stable over the years, and it stays. Methane, after around 12 years, turns into CO2. So you see, where did we have the cursor? Here. You see here that it 12 years and then it's like CO2. Now, if you focus on the first 20 years, because this is compared to based on 100 years base of comparison. Now, if you look at 20 years, you still have, that's the lower graphs, you still have 12 years of lifetime, atmospheric lifetime of methane, and then it turns into CO2. So then the 12 years will be much more powerful. So then you have not 25 times, but 72 times. So the shorter or the closer to 12 years you compare CO2 to methane, the more powerful the impact. So if you compare then two major sources of emission, one fossil power plant, a coal-fired power plant, and a coal mine ventilation shaft, and say that after a certain time you have a major emission reduction right here. Say you reduce it by 90%, the emission. The CO2 emission from this plant will remain in atmosphere, and then it will slowly increase with a new emission. If you compare that to a coal mine, to Vam emission, for example, you have a 12-year buildup of methane, and that will remain in atmosphere. When you reduce by 90%, you will have an immediate reduction in the impact, and after 12 years, you will have the new level of emission, which is like, in this case, 10% of the new one. So you will have a very quick impact. So that means that methane is an opportunity for major reductions of greenhouse gas emission impact. So let's look at technologies. We're talking large volumes, like 1 million cubic meters per year. We're talking very low, extremely low CO2 content. So technologies having been tried, I mean, the best way is if you have a power plant close to a ventilation shaft, then you can use the ventilation air as combustion air, and you will get the extra benefit of the energy in the 1% or 0.5% methane. But it's very rare to find such installations close to a ventilation shaft. So if you do find that, congratulations, that's a very good option. There have been trials on lean gas turbines, and they have typically managed to come down very far, but below 2-3% is difficult. And also the volumes is an issue. So the volume of a ventilation shaft is so large, so you would need a lot of turbines to handle that. Concentrators, very interesting. If you can increase the concentration from 0.5% to maybe 20%, you have a very good case. But the methane molecule is so small, so it's difficult to handle in concentrators. There are trials, some looking promising, but nothing really successful yet. And then you have industrial oxidizers. This is where you find the so far most successful installations, or the successful installations. And there you have RTOs, regenerative thermal oxidizers, you have catalytic oxidizers, and you have recuperative. I won't go into those different techniques, but if you look at these, recuperative is not interesting. Regenerative catalytic can be interesting, but the catalyst is often sensitive, and you can poison the catalyst, and at some point you need to replace it. So at this point in time, regenerative thermal oxidizers are the most interesting proven technology. If you look time-wise and relate it to the climate conferences, the Rio conference decided that there will be, on the establishment of the UNFCCC, you have the Kyoto conference, which decided that there will be a trading in carbon credits, and that was officially launched in 2005. You have the Copenhagen conference, which failed to extend Kyoto, and then you have the Paris Agreement. So looking at the trials of VAM installations, the first one was actually in 1994 in England. Small unit that showed that it was possible to operate an RTO on VAM. Then you had, 3 years later, there was an Australian trial, also a small unit, showing that it was possible to use the energy developed when you oxidize VAM, use that energy to create steam. And then you had a large-scale installation in the US in 2007. And that was actually operating on abandoned mine methane, being able to demonstrate the technology in different concentrations. Then you had a number of installations. I will not go into them, but you see by the size of the arrow how big or how large the installation was. If you look at it geographically, these are the commercial size VAM processing installations that have been installed and in operation. Most interesting, I would say, is the VAM power plant in Australia, processing 250,000 cubic meters of ventilation air with 0.9% methane and generating electricity. This was in operation between 2007 up until last year, when it was closed because they moved the longwall. Now, looking at these, how many are now in commercial operations still today? Not so many, only 2. So you have one in the US and one in China. And why is this? Well, the closures are due to moving the mining activities, and most of them due to failing values of carbon credits, because all this is based on the value of reducing the methane emissions. So briefly, how does it work? Well, you have methane, you have oxygen present, you raise the temperature, you will have a reaction where the methane and oxygen turns into water vapor and CO2 and release energy. So basically, if you raise the temperature of methane with oxygen present, you will have a complete oxidation around 900 degrees C. And this is done in, the most simple explanation or description is that you have a very, very well insulated steel container. It's filled with a ceramic material like gravel. In the middle, in the center, you have electrical heaters. You heat it up to 1,000 degrees C, then you start passing the ventilation air through the box. And as the air comes to the center of the box, it will have 1,000 degrees because you have a very efficient heat transfer between the air and the media. Now, 1,000 degrees with oxygen present, of course, all the methane molecules will have oxidized. So as the air continues through the box, it will heat exchange, leave in the heat, and then out in the atmosphere. So you pick up heat coming in, oxidize, leave heat going out. So you're slowly moving the heat zone in the direction of the flow. So therefore you change direction of flow every few minutes, and you have the hot zone, oxidizing zone, going back and forth a little bit in the center. There's no catalyst because this is the natural oxidation temperature of methane. Now, that was a single can oxidizer. You can also split it up. So you take half the bed, you flip it over, and you have a combustion chamber in the middle. And then typically you don't start it with electricity, you start it with a flare. So you heat the combustion zone up to 1,000 degrees, you pass the ventilation air through, going back and forth, and then you have the same principle. There are 3 can systems too. They tend to be more expensive. You can get higher degree of cleaning. I mean, every time you change direction, there's a small section in the incoming air that will go out uncleaned. So it's a technical matter of how you want to optimize it. Typically you would, processing 1,000,000 cubic meters per hour is a lot. So you do a configuration which is rational and you multiply it in a modular fashion. You need only 0.2% methane to keep the oxidizing process going. So if you have more than 0.2%, then you can utilize the excess energy. And you can utilize that for heating. You can utilize it for making steam and then running a turbine, as was done in Australia, creating electricity. If you have heating, you can generate cooling. So it can be quite flexible depending on the local conditions. So looking at a VAM project, you're looking at the most important parameters are the total cost for the investment, the average VAM concentration, because this is air processing equipment. So if the concentration is 0.2% or 0.9%, doesn't really matter for the equipment, but it matters very much for your economics. So the concentration is important and the value of reducing the emissions. So what are you being paid for reducing emissions? An example, 800,000 cubic meters of ventilation air per hour, 1% methane. You could generate 72 megawatt of thermal energy, which could be converted to around 20 megawatt of electricity. If you reduce the methane concentration to 0.6%, you still lose the 0.2 to the oxidation process. So by going down 40%, you lose half of it. And then you can have a cooling water circuit running an absorption chiller. You lose a little bit on the conversion, but you gain a lot of cooling. So let's not get too deep into this. These are just tables showing how much energy you can retrieve from this technology. So depending again on concentration, 0.3, 3 megawatt, 0.9, 18 megawatt, and this is if you get the heat straight from the bed. The difficulty is to find a very large consumer of energy close to the mine shaft. Normally it's enough to have a secondary heat exchanger on the exhaust, and then you can still get a lot of energy out, which is normally quite sufficient. Then you can make electricity. There you have numbers for that. This is a table with examples where you have, on this side you have number of cubic meters of air processed, you have the concentration, and you can see that if you're processing 125,000 cubic meters per hour at 0.3% methane, you will generate around 40,000 carbon credits. Whereas 1 million cubic meters at 0.9, you will be at close to 1 million million carbon credits. And these are indicators showing that basically you should be looking at concentrations around or above 0.5%. You see, the higher your internal rental of return. And the value of carbon credits should really be around 12 to 15, 16 euros per ton. Then you have a very good case. You have a quick payback time. So when you look at your installation, you want to optimize it. Well, you look at what concentrations and volumes you have in the drainage. You look at the concentration of the ventilation air. I would say you first look at installing gas engines, because the most cost-efficient way to use the mine gas. And then you look at, if you really want to process to reduce the emissions from coal mining, then you have to address VAM, because it represents like 70% typically. So if you have a concentration which is close to 1, which is often the case in Poland, then you might look at generating electricity. And then you would be looking at taking some of the drainage gas and using that to stabilize the concentration in the VAM. And you might even look at increasing it from 0.6 to 0.8 maybe, because you will have a full impact of that increase. So VAM in Poland, we're looking at high concentrations compared internationally. In some countries where they don't have full control of the underground air handling in the way you do in Poland, they cannot allow the VAM concentrations to be high. So you will see in some countries VAM concentrations of 0.1. And then there's nothing we can do. But in Poland, I've seen a number of mines where you have VAM concentrations above 0.5%, 0.7, 0.8, and then you have a very good case of looking at processing VAM. In Poland, you also have a very good engineering experience from utilizing drainage gas, coal mine methane, for electricity as well as for heating and for cooling. On top of that, Poland is within the EU responsible for clean coal technology, low emission coal technologies. So I'd say Poland is a perfect place to start looking at VAM processing. So summing up, the conclusions from all this is that methane is a very powerful greenhouse gas, especially if you look at it short term. It has a short atmospheric lifetime, and that means a quick positive effect on climate change. And VAM represents a major single source of emission. So one outlet in a big mine shaft can have the same effect as the emissions from 500,000 cars. So Vam Processing, there are a couple of experienced RTO or regenerative thermal oxidizer suppliers who can provide proven Vam processing solutions. Then there are more suppliers entering the field. They are not as experienced yet, but these experienced suppliers, they have supplied thousands of similar units to other industries. But the newcomers, in time, they will also learn, so they will also be eligible suppliers to Vam Processing. And there will be more technical solutions. I mentioned concentrators. So there will be other technical solutions in time. Now, for the best feasibility of a VAM project, you should look for VAM concentrations around 0.5% or more. You should look at possibility to enrich the ventilation air, where you can take drainage gas and feed it into the ventilation air for the purpose of reaching 0.5%. You should first look at possibilities to utilize thermal energy close to the mine ventilation shaft. And as Dr. Skiba said, you're going deeper, and as you go deeper, you will be needing more cooling. So that could be a very interesting aspect of utilizing the energy. Use it to do cooling. And the most difficult part is you should be looking for how to get a good value to reduce the VAM emissions in the form of carbon credits or similar. Finally, you should optimize your overall emission strategy between processing of drainage gas and processing of VAM. And I would say Poland is perfect for demonstrating VAM solutions. Even combined as tri-generation, you can have electricity production, you use the cooling water from the turbine to generate heating, and you can use that heating to drive an absorption cooler, and you will have cooling. That's a brief overview of what you can do with VAM and where the development stands today. Thank you. Dziękuję.